Okay. All right. So today we're going to continue our discussion about not this one here about phaser, but we briefly talk about like how you do the calculation for the phaser because most of the things is the same as this thing that you learned in the chapter 4, except the everything start to have a complex number instead of the real number. You use the no voltage or mesh circuit current method. They are all the same. You write all the equation, you solve the equation, and you find the answer. I want to start with this to tell you what happened after today. So we are on the 13th week until the last week is the finals week. You still have another exam on the 14th week, which is next Friday. I did open the study guide, as I mentioned before. You should look at the study guide. It's going to cover material. Actually, it's going to cover from chapter 9 to 12, because if you don't know about how to transform into a phaser, you don't even know how to do the 9.5 to 9.9. So it pretty much cover chapter 9, 10, and part of 12. The 12 is the Laplace transform. We will start to talk about Laplace transform next week. You're supposed to learn this one from your differential equation. We're going to start with an kind of like a review, starting from the next week. We will talk about the Laplace transform, and then we will talk about inverse Laplace transform. Inverse Laplace transform will not be on your exam. We will only look at the Laplace transform, so you have to know how to do a Laplace transform. For this Friday, we have a lab, which is the power factor lab. That will be our last lab. So after that, we actually have another lab, but I think you guys probably need a review. So the last week of Friday, before the final exam, we're going to give you a lab just talking about the examples, and there will be an online section. And I do encourage you can all come to this lab, and we can work on some of the problem. If you're not familiar with any of them, then we can focus on those problems as well. Since the Laplace transform is kind of the last new stuff, well, actually it's not new, but when we solve the circuit, it will be probably a little bit new to you. I probably will spend more time to talk about Laplace transform at that moment as well. After the 14th week, on the 15th week, we actually is going to show you how you can apply Laplace transform in the circuit, and we will do some example to help you to understand how to analyze that. For the finals week, the final exam is on the last day of the semester, so it's going to be comprehensive. You can click on the study guide. You can see the study guide. There's a list of the questions that I propose to give to you. And in the final exam, I'm going to allow you to prepare your own formula sheet. So you can prepare 1-page double-sided formula sheet on yourself. No workout problem, but beside that, whatever you think that you need, then you can put that in that formula sheet. I will provide you with the Laplace transform formulas. There is a Laplace transform table, inverse Laplace transform table. There's another table in the chapter 13, which help you to analyze Laplace circuits. So those 3 tables I will provide. Other than that, that you prepare your own formula that you think is important to you. Okay, are there any questions about this? As I said, your final exam, because it's comprehensive, for those of you still doesn't have a good grade on all the exams, if you do much better than the rest of the exam, I will use your final exam as your exam score. So if you got exam 50, 60, but your final is 70 or 80, then I will use 80 to be all of your exams, which is lower than the 80. So it will be help you to bump up your score. But it's comprehensive, so you might need to spend some time to prepare that. Okay, homework. Still, a lot of people haven't started work on the chapter 9. Then you're gonna lag behind because we are going to finish chapter 10, and chapter 10 is based on chapter 9. Starting today, we're going to talk about the power. So try to work on the homework as soon as possible. And if you are late, I sent an email out. The deduction is 2% per day. It will never deduct more than half. So if you already passed the due date a long time ago, you can still submit it. It will help you on the preparing for the exam as well. So that will be my last advice. Okay. If you have questions, let me know. Otherwise, I'm going to move on to chapter 10. Okay. So we started to talk about chapter 10 in the lab. And the chapter 10 is about the power. Now, for the AC circuit, how do you find the power? Because the current and voltage keep on changing. Then if you talk about power, that power probably is what we call the instantaneous power. It's the power at that moment of the time, and you take the measurements of the voltage and also the current, you multiply them together, you got the power, which is instantaneous power. But it's not the whole story. That power is actually not the power for just resistor. If you talk about the power in the circuit, and if you have not only resistor, but also the capacitor inductor, they also have power. Then how do we represent the power of those things? Well, since everything in the phasor represented by a complex number, power also can be represented as a complex number as well. So you're going to hear a lot of different terminology today. We will tell you what they are and how do you do the calculation, and how you identify the sign of each one of the power. Okay, so what is the power analysis? The power analysis is the same as you did in the DC circuit. Once you solve or you analyze the circuit, what you try to do is actually to find the V and the I. What is the voltage in the circuit? What is the current in the circuit? And if you have different components, then everything depends on the V and I on the elements. Then we have a DC power, we have an AC power. The DC power is a fixed number, right? DC is a constant. And what is the unit for the power? Well, it's in watts. Watts meaning joule per second. Okay, so that's the watts represent the power. Well, the AC power is a combination of DC with a sinusoidal. Okay, it's not just simply a number, it's an equation. Actually is a time dependent equation. So how do we find that? Well, two things. First thing is that we want to find the value, and the second thing is that the unit is a little bit different from the DC circuit as well. The DC, you only look at the power, which is in watts, but AC, we have several different names for different kind of power, which we will tell you from the following equation. The following equation is the instantaneous power. And I said, how do you get that? Well, if you look bottom here, the power definition is simply the V times I. And what is the V? What is the I? Well, you can assume my voltage and the current in this kind of form, this is a like general form, right? V sub n, I sub n represent the maximum amplitude. It's different from the RMS value, okay? So it's different from RMS. So remember this, because when you, especially for this chapter, when we talk about how do you find a power, there's several different equations, depends on are you using the maximum value or the RMS value. And be careful when you look at the problem, sometimes they give you the maximum value, sometimes they give you RMS value. They are not the same. They have some difference. So make sure that you look at what the value is given. And then normally we represent the sinusoidal as a cosine function. Even if you represent a sine function, you can write it as a cosine function as well. There's a phase difference. Theta V represent the phase of the voltage, right? And theta I represent the phase of the current. They don't have to be the same, especially if you have a capacitor or inductor. And you multiply them together, you're going to get the equation as we show you at the second line here. And the second line that we told you, this line tells you like two things. One is this part here is a constant, which is what I say, this is like a DC, right? It's a fixed value. And this fixed value, it doesn't, it's not a function of time, okay? Because this is a constant, so it's not a function of time. It doesn't depend on time. It is also not a function of omega. It doesn't matter how fast that you oscillate the signal, this number doesn't depend on the omega as well. However, the second term that you see, it carries the same amplitude, right? This amplitude and this amplitude is the same, but then it's also a cosine function, but then it depends on 2 omega. Okay, it is a function of time. It depends on the omega. The frequency is 2 omega. It's not omega itself. Okay, this should be like the radial frequency. It's not like the f. If you're doing the f, then you have to divide by 2 pi. So the oscillation is 2 times faster than the V and the I. That power is oscillate faster than the current or the voltage itself. The other thing that you notice in here is there is a theta V minus theta I. Now what this is the phase difference, right? Phase difference between V and I. So the phase difference between the voltage and the current. And that's what the equation tells us just by looking at the equation without doing any of the calculation. But this is the equation tells you how they are related. Now, if we draw a picture of that, then we show you this in the lab as well. Let me just draw a picture real quick and here to see what it looks like. This is one of the line, and we also have a horizontal line here. Okay, now there is a level. That level is the level going from here to here. This level is more like the DC value. So this one is what we call the DC value here. And this value is this one here. And then you also have some oscillation, right? So that means the actual wave is going to go like this. And this is your power. This is your P sub T. Okay, the oscillation itself is coming from this the second term in this power equation. So if you wanted to write this one here, this will be the V sub n, I sub n divided by 2 with a cosine 2 omega t plus theta v minus theta I. This will represent that equation, that curve over there. And that level here is the level which is that constant that you should see on the screen. All right, so it looks like this one is a little bit complicated. And if you look at the book, they will also continue to derive this equation into 3 terms. And so this one here, the cosine 2 omega t, you can represent that using the trigonometry identity will be a combination of the cosine and sine. And this is what we represent to you at here. So without detailed derivation, if you're interested, you can look at the book, which we will not do that. The power turns out to be 3 terms here. The big P and the big Q, okay? So what does the big P and big Q represent? Well, the P part is actually the cosine part, which is this whole thing over here. Okay, this whole thing is your P. And if you represent that, okay, I actually write it over here. So here is what the P and Q is. Now, the only difference is that it becomes from the cosine function into the sine function, but they all have the phase angle difference, the theta V minus theta I. So you kind of separate the amplitude out of some like something that will change with time, right? So all these two, P and Q, are constant. P and Q are constant. It doesn't depend on omega. It doesn't depend on time. And we call these two things with a different name. Well, let me give you the name first, and then we will explain what that is. So this P here represents what we call the real power. Sometimes we will call this is the average power. So P is the real power or average power. What that is that it is the power consumed by the resistor. So this power has the unit, which is the watts. Okay. What about Q? Well, the Q is different from the P. The Q is what we call the reactive power. The reactive power is the power either stored or released by the capacitor or an inductor. Okay, so that they're not actually generated by the capacitor or the inductor. It's the temporary power stored in those devices, and they can either take the energy in or they can release the energy as needed. Because they are different, then we want to distinguish these two. So the unit in this one is also different. This unit is called VAR. So if you see var, when we say var, that means this power is the power which is reactive power. Okay, it's not like the real power that actually consumed by the resistor. And that's the main difference. So here is that you have real power called watt, called the real power or average power, and you have imaginary power, which is the Q. Um, there is another power, which is actually the total power of this. And that total power is what we call the complex power. Okay, so what is a complex power? The complex power simply means let's just put these two power together in a complex number, then that will be equal to your real power or average power plus the J times your Q. Okay, so that make these two become one, and which is the total power, and this total power is what we call the complex power. Is a combination of the real power and the reactive power, and in a complex form. Okay, we will go back. We will come back to the complex power next time, but I want you to understand the different terminology. Well, and also. This is a kind of a weird thing. The unit for the complex power is neither the watts or the var, is actually called var. So the unit for this one. Okay, all these three things has a different unit. P is the real power, is in watts. Var is the reactive power. Var is the complex power. So that is the three things I wanted to start with. Okay, any question about this? All right, we will do an example after this, but let's look at the situation. What happens if you have a circuit which only have a resistor and you are supplying with an AC circuit? So this kind of circuit is what we call the purely resistive circuit, that you only have a resistor into the system. And if you do the experiment, then you can measure the current, the voltage, and the power. And if you look on the right-hand side, before I write any of the equation, if you look at the right-hand side, you can see the red color represent the current, and the blue color represent the voltage, right? And what I tell you is the current and voltage, they are in phase. Okay, so they are in phase. There's no phase difference. And there's no phase difference was because the impedance is a real number. If impedance is a real number, you are not going to induce any of the phase difference because the real number has a phase angle that is equal to 0. So the voltage and the current is going to have the same phase, right? So here, if we represent this one as the impedance, this is a Z sub R. Since this is going to be a real number, we can represent this one as the R with a 0 degree. And then you have a phasor I, you have a phasor V. So this is a phasor I, this is a phasor of V. And then you can find their relationship by writing the Ohm's law. V is equal to I times the Z. And what is the Z? Well, Z is an R was a 0 degree. So if your I is going to be I sub n with an angle theta I, and you say, oh, this one has the V sub n was a theta V. In order to make these two equal, then you have a V sub n theta V equal to I n times R with an angle theta I plus 0 degree, right? The multiplication. which means theta V has to be equal to theta I. So they are in phase. Now, what about the power? Well, the power, you have to use either the I squared times R or V squared divided by R. And because you use the square, you can see all this power go to the top, right? So this curve, they all flipped from the bottom to the top. They don't go up and down because it's a square, okay? And that represents the power. Now, pure resistive circuit is the simplest circuit. And this is the circuit that we analyze quite a bit, and it's nothing really need to worry about. The things that people make a mistake is the reactive power. So, if you look at this, and what is the actual power is going to happen in here if you have this situation. If these two are in phase, let's look at the value of the P and Q. Here we have a P and Q on top, right? So if in phase, theta V equal to theta I, and our P become what? So theta V equal to theta I, meaning theta V minus theta I equal to 0, and cosine 0 is 1. So it turns out your P is going to be VNIN divided by 2. Okay, what about the Q? Well, the Q is going to be sine 0 when sine 0 is equal to 0. Yes. So what is the power equation then? Then your power equation, well, I should write P sub T. I should write P sub T. So your P sub T become what? And look at this equation here. We separate this into 3 different terms. You're going to have the P, this one here. This is a different from the P, all right? So this is simply represent this one right here, the real power. So I have a real power, and what? Do I still have the second term here? Well, I have the P cosine 2 omega t. So I do have this, okay? Do I have the Q? No, I don't have Q, and that's it. So this is the real power if, well, this is a power for the resistive circuit. If you wanted to know what is the power of the resistive circuit, it doesn't mean it only have one fixed value because it's oscillating. So the power also oscillating as well. But this is the value of the power in that situation. This is actually the instantaneous, okay? This is instantaneous. This should be the AC resistive circuit. Okay, that is the first one. Now let's look at the second one. The second one that we look at is inductive. So what is the inductive circuit? You only have an inductor. So here is the inductor that you have. And what is my Z for the inductor? There's a J omega L, okay? If you do the homework, you should be familiar with this. Then Y over J omega C is the Z sub C. And what does this one represent as a phasor? If I represent this as a phasor, this will be omega L with a degree of a 90 degree. The positive J is 90 degree, negative J is negative 90 degree. That is the degree of my pure inductive circuit. Again, I have I at here, I have a V's over here. You can use the Ohm's law to represent that. So if I represent this one with the voltage of this inductor, and that will be equal to this current and multiply with my Z sub L. Okay, now V sub L is the Vm. Actually, this is the power goes in, right? If I represent this one here will be negative 90 degree if you use the cosine angle here, right? This is a sine angle, then you are going to use negative 90 degree. What about the I? Will the I still be the same angle? I don't know. Let's just write the I in terms of magnitude with certain degree. And what is the Z sub L? Well, the Z sub L is omega L with a 90 degree here. And on the right-hand side, I can combine these. There will be I sub n omega L with an angle theta I plus 90 degree. Okay, so what does that tells me? Well, that tells me if I say, well, if this is not 90 degree, let's say this has some angle. By assuming this has a more general, let's say this has a theta v here. Then I'm going to replace this one to be a theta. Well, let me, instead of using the sine, let me just use cosine because this is more general. That will be more like our situation. If this is a cosine and I have a theta v here, and then this is the expression to represent how they are related, then you can make a more general form like this. So this one here, v sub n theta v equal to I and omega L theta I plus 90 degree, which means theta V equal to theta I plus 90 degree, or theta V minus theta I equal to 90 degree. And that means there's a phase difference of 90 degree. And which one lead and which one lag? And how do you determine which one lead, which one lag? And you look at the complex plan that we told you before. This is a complex plan. If you say I is along this direction, if this is an I direction, and your V is going to be 90 degree because I is in 0 degree, right? So your V will be here, such that this is your theta V. And you minus theta I will be 90 degree. Now, which one is the lead? Well, the one goes forward in the counterclockwise direction is going to be the lead. So this one lead and this one lag. So this will be V sub L is going to lead the I sub L by using this way to look at that. All right, so let's look at the powers. So what's going on with power in this case? If you have a purely inductive, and my power is this here. Now theta v minus theta I is 90 degree, right? If that is 90 degree, cosine 90 degree is going to be equal to 0. Sine 90 degree is going to be 1. So now you have P equal to 0 and Q equal to 1. And your Q is equal to 1. Oh, so this is be sine 90 degree. And then what is the instantaneous power of this one here? This one is equal to this P plus P times cosine 2 omega t plus Q sine 2 omega t, right? I think so here, right here. Okay. Oh, it's minus. So here is minus. And because this is a zero, this is a zero, and this is what you have left. This is the power, instantaneous power of a purely inductive circuit. All right, any question about this? And if not, I'm going to skip the conductive. It's almost like the same, except the your phase difference. If you look at this one, the phase difference, the theta v minus theta I is going to be negative 90 degree instead of positive 90 degree. And your power, the instantaneous power of this case is going to be a negative Q and the psi 2 omega t. Okay. So it's the psi changed in this situation. So the one before, you are going to have a positive, and oh, this one should be a positive actually. Okay, because your Q is going to be negative 1. Okay, and you can look at how the lead and lag is the same thing that we did before. Okay, any question about this? All right, the next thing here before I go into the example, I wanted to give you an idea which is called the power factor. So what is the power factor? It turns out the angle difference between the V and I plays an important part. Because if this angle is greater or this is a smaller, you are going to change the cosine theta value. And we know cosine 0 is equal to 1. And cosine 90 degree is going to be 0. If you have a cosine 0 degree, and in our circuit, then we have a cosine with a theta v minus theta I. So that means if the theta v equal to theta I, you will have if you have these two equal, you're going to get the maximum real power. And what is the real power? Remember, the P is the real power. So how do you get the P to be maximum? If you wanted to get the P equal to maximum, you had to make the theta V equal to theta I. Okay, so the theta V equal to theta I is going to give you the maximum real power. Let's take a look here. So here is the real power. To get this value to be maximum, you have to make the theta V equal to theta I in order to get the maximum real power. Okay, and so that means if the cosine theta V minus theta I is equal to 1 is the maximum real power. And we call this one here power factor. So the power factor is the cosine theta V minus theta I. And that's how we define as the power factor. Okay, you try to make it equal to 1 or more or close to 1 to actually get the real power. Now, why do I keep on saying the real power? Before we get into the complex power, I just want to give you an analogy to tell you about what does that mean to us? What do we mean like your power factor? Why do I need a power factor to be close to 1? Well, we can use a triangle to represent the power just like you represent a complex number. Now we are representing a complex power. The S here is what we say the total power. Another name for that is the apparent power. Apparent power is the S, is a complex power. It's a composition, it's a combination of the real power and the reactive power. Where the real power is on the real axis, and the reactive power is on the imaginary axis, which is on the y-axis. The angle between is the theta v minus theta I. And we try to make the theta v minus theta I equal to 0. That will give you the maximum power, and which is actually the ratio between the P over S. That is the cosine theta, which is the cosine angle difference. And the people use the beer to be the analogy for the power. So normally the circuit that we have is not purely just resistive. We have an inductor and capacitor in the circuit. And the beer itself is what we say the real power. So this part is what we call the real power, is the beer that you actually have. And this frost over here it looked like the beer, but it's not, right? So this is a kind of wasted. It's not really the power that you can use. However, you are going to demand the power to be this much, because these parts can be real, depends on how you pour your beer, right? Or how you draw the beer. You might going to use that much of the beer if you make the power factor to be the maximum power. So the demand power is that when you want a utility company to give you the power, you won't say, I only wanted to have this like 80% or 70% of the power, because you might actually use more power than you normally use than the average. So you want to demand the maximum power. But the real power is the power actually being used. So, so how the power company charge you is they charge you not the useful power, they charge you this. And if you are a company and they charge you this, what you would do? What you would do is try to make the demand power to be close to your useful power. You try to make the power factor to be close to 1. So you don't waste any of the power being charged, but you're not using it. So that is what this 3 different power means. How can we improve the power factor? I put this one over here, but we're actually going to discuss this in our lab and also in our next lecture. So I just leave this one to you, and we will talk about this next time. So to make the power factor to be improved, normally you will modify the circuit by adding a capacitor. A capacitor can actually help you to improve the power factor. And that was because most of the circuit that we have is an RL circuit, and we need to put a capacitor to compensate the power lost because of the inductor. Okay, any question about this topic? All right, let's look at an example. Maybe the example will help you understand the material here. Okay, I'm listing several equations that we talked about before. This is the one that is most important. The instantaneous power is 3 components, right? The big P plus the big P times the cosine 2 omega t minus Q sine 2 omega t. And here's the P. This is the real power or average power. Q is reactive power. Power factor is the cosine theta V minus theta I. You can find the power in phasor as well. This one we will talk about this next time, but just remember this is the way that you find the complex power. I'm going to use these to just solve this problem here. So I have the device here. This is the device. This device, as the current goes in, and voltage look like this. A polarity, one on the top and bottom is negative. If I make the V and I equal to this equation, how do I find the power? Okay, so this is the problem that we want to solve. This is a very simple one. Just by looking at this one, if you wanted to find the power, you better to make it into a phasor, because all the real power and imaginary power here, the reactive power, depends on the theta V and theta I. So let's find out what is the theta V and theta I. So what is the V here from this one here? That's 100 with angle of 15 degrees, right? What about I? That is 4 with an angle negative 15 minus 90 degrees, right? That's what we told you before, how you do a phasor transformation. Sine, you have to minus 90 degrees. So that means this is a 4 with negative 105 degrees. Okay, so what that means is my theta V is 15 degrees. My theta I is going to be negative 105 degrees. Okay, now, how do I find my real power? Well, the real power, I have an equation here, which is a V sub n, I sub n divided by 2 times cosine theta V minus theta I. What is V sub n? V sub n is 100. I sub n is 4 divided by 2, and cosine theta V 15 minus 0.105. Okay, so then you got the real power. The real power is going to be, that will be 200, right? Times my cosine negative 120, oh no, it's not negative, 120 degree. Positive 120 degree. Okay, and if you use your calculator to find the solution, this one will be equal to negative 100. And what is the unit for this? The unit for this is watt. Okay, the real power is in watts. What does the negative means to us if power is negative? Is it delivering or taking, consuming? It's a source. Yeah,
delivering.
So it's, yeah. It delivers power. It delivers power to our circuit. Okay, let's find the Q. Same thing, VMIN divided by 2, but this will be the sine theta V minus theta I. This is the Q. In this system here, do we have a Q? This is the sine, right? Everything is in here. This will be sine 120 degree. Okay, if you do calculation with your calculator, this one turns out to be 73.2. And what is the unit for the Q? This one here, var. Okay, so 173.2 var. That is the power of the Q. Okay, now this is a positive, right? Meaning, and it's going to take the power, is going to consume the power. If we ask you, what is the power factor for this circuit? The power factor is the cosine theta V minus theta I. So that would be cosine 120 degree. And this one will be what? 0.5.
Negative.
And negative, yeah. Okay, now you wonder, well, what does negative means? Okay, now what do we mean by negative and positive? So the power factor is it represents like a phase angle. So if your theta V minus theta I is larger than 0, that tells you V lead I. If theta V minus theta I is less than 0, then it will be opposite. The I will lead a V. So the negative simply tell you whether this one is the lead or this one is the lag. Another way you can look at this is that you can make a picture of that, right? So if you make a picture of that and then let's say your I is at here, so angle is 0 degree to make things easier, and then this will be your V. And just tells you how much degree this one is lead and which quadrant this one is going to be. Okay, question about this. Let's work on another one here. So just make sure that you comfortable about finding these. So now we got the other set of the V and I. So the first one you do is the change all these to a phasor. So there will be 100 was minus 45 degree. And your I is equal to 20 with 165 degree. What is the unit for the V phasor and what's the unit for the I phasor? It's the same as your time domain. Remember, the impedance has the unit of omega. So they have the same unit. Okay, so once you have this one, then you know the theta V, you know theta I. Then you can find this P. The P is 100 times 20 divided by 2 with a cosine minus 45 minus 165. And that's how you get this power P. And same thing, you do the Q, 100 times 20 divided by 2, and then this will be sine minus, that will be 210, right? Minus 210. Well, the minus 210 is similar to what angle is that? 180 with a okay. Minus. You can also make it to the positive, right? So this is a negative 180. Negative to 110, there'll be 30 degree here, there will be 150 degree here. Right? So this is also equal to 150 degree. Okay. Then you can use the same way to find the power factor by using this. Okay, any question about these things here that we talk about today? All right, if not, I'm gonna stop at here. The next time we come back. Oh, by the way, there's another topic that I didn't put a lot of. So there's another called the appliance rating. So if you go buy any of the appliance, they always going to have a yellow sticker to tell you how much energy this device will consume. And the power consumption is in terms of the kW per hour, kWh, meaning kW per hour, how much energy will be consumed. Yeah. So let's say if you have an appliance, and the rate is 36 kWh, and the power of the when there's an operate, if you run this appliance and when you run it and the power it is running is let's say 12 kW, then what this means in this 36 kWh is if you use the 36 kWh divide by this 12, this is 12 kW, and that means you're going to use this one for 30 hours, right? But this number is like a yearly number. That means actually this is a yearly used power. So that means 30 hours per year of the operation of the component and using the 12 kW. And that's how much total power you're going to use for a year, which is 36 kWh. And this is the number, the kWh is the number that power company actually charge you. So you want to try to reduce this number as much as possible because this is how they're going to charge you. All right. I'm going to stop it here unless you guys have any question. If not, then I'll see you on Wednesday, and please start work on your homework on chapter 9 and chapter 10 because your next exam going to emphasize on the chapter 9 and 10. So make sure that you do all these things, and it's nothing new. Again, nothing new. Most of the things is still depends on your skill of analyzing circuit using KCO, KVL, node, mesh, source transformation, Safin and Norton, and superposition. All right.
I have a question. How
Yes.
did you get 30 hours per year instead of 3 hours per year?
Oh, yeah. I think this should be 1.2. Sorry.
Oh, okay.
Okay.
Thank you.
Okay. I'll see you next time.